Have you ever wondered why everything just seems to run out of steam? You push a box, it slides for a bit, and then it just stops. You roll a ball, it slows down, and poof, it stops too. It really makes you think the natural state of everything is to be perfectly still. But what if I told you that what we see every single day is actually hiding a deeper, more fundamental truth about how the universe really works? Yeah, let's unpack that.
So here's the game plan. We're going to start by looking at our own faulty intuition about motion. Then we'll dive into the law of inertia itself. After that, we'll unmask the hidden force of friction, explore what inertia and equilibrium are all about, and finally, we'll zoom way out for a big, universal perspective.
All right, let's kick things off with what we think we know. See, our intuition about how things move is built from a lifetime of just watching the world around us. But it turns out that experience has been misleading us.
I mean, this is the big question, right? You give something a shove, why doesn't it just keep going forever? It really truly feels like everything has some sort of built-in desire to just come to a halt. But is that what's actually happening?
This one single observation shaped how people thought for literally thousands of years. It just seems so obvious, doesn't it? To keep something moving, you've got to keep pushing it. But as we're about to see, this simple idea misses something absolutely crucial.
And that brings us to the law that completely flipped our understanding of motion on its head. This is Newton's first law, but you probably know it as the law of inertia. And what it does is describe the default behavior of, pretty much everything in the universe.
Okay, now the language here is super precise, and that's what's so important. It doesn't just say in motion, it says at constant velocity. That's key. It means a constant speed and a constant direction, so a perfectly straight line. And it will only change if a net external force messes with it.
So let's boil it down. The natural tendency of an object isn't to stop. Nope. It's to maintain the status quo. If it's sitting still, it wants to stay still. If it's moving, it wants to keep moving in a straight line at the same speed forever. Motion itself doesn't need a cause. A change in motion does. That's the game changer. So that brings us right back to our original mystery. If objects want to keep moving, why on earth do they stop? Well, the law just gave us the answer. There has to be a cause. There has to be a force. And that leads us to the great, unseen villain of motion here on our planet. Friction, that's the culprit. It's that force that pushes back against motion whenever surfaces are in contact. It's the reason a box stops sliding and a ball stops rolling. It is that external force that our intuition tricks us into thinking is just an object's natural desire to stop. Let's do a little thought experiment. Ready? Okay, first, picture sliding a block across a rough carpet. It stops almost right away, right? Now imagine sliding it across a smooth, polished wooden floor. It goes way farther. So what if we could imagine a perfectly frictionless surface, like magical ice or something? What happens then? Well, that block would just slide and slide in a straight line at a constant speed forever. And this is where it clicks for so many people. An air hockey table is about the closest we get to seeing a frictionless world. You turn the air on, and that little cushion of air lets the puck just glide effortlessly. It's almost perfectly obeying the law of inertia. It just keeps doing what it's doing until, bam, it hits a wall, which is, you guessed it, an external force. Okay, so we've established that objects resist changes in their motion. Let's dig a little deeper into that property, inertia, and see what happens when all the forces acting on an object are perfectly balanced out. Now, here's a really important point. Inertia is not a force. It's a property of matter itself. Think of it as an object's stubbornness. And how much inertia, how much stubbornness an object has is determined by just one thing, its mass. The more mass, the more stuff, and the more stuff, the more it resists being sped up, slowed down, or turned. Think about it like this. It's pretty easy to stop a rolling basketball, right? It has less mass, so it has less inertia. But now try to stop a rolling boulder. Yeah, that's a totally different story. Its huge mass gives it a ton of inertia, making it incredibly difficult to change its state of motion. So, what happens when forces are acting on something, but they completely cancel each other out? Well, that's a special state called equilibrium. The net force, the overall combined force, is zero. And what does Newton's first law tell us? If the net force is zero, there is no change in motion. The status quo continues. Now, this is where it gets really fascinating. There are two kinds of equilibrium. A parked car, for example, is in static equilibrium.
Gravity pulls down, the ground pushes up, all the forces are balanced, and it just stays put. But, and this is the really cool part, a car cruising down the highway at a constant speed is also in equilibrium. The forward push from the engine is perfectly balancing the backward drag from friction and air resistance. The net force is zero, so its velocity doesn't change. We call that dynamic equilibrium. Wild, right? So look, this law isn't just about pucks and cars here on Earth, not at all. It's a fundamental rule that applies across the entire cosmos. So let's zoom out and see how this whole thing builds into a truly universal law. Okay, a quick technical bit, but it's important. The law of inertia works perfectly from any viewpoint, or as physicists say, reference frame, that isn't accelerating. So what does that really mean? Well, for all practical purposes, a viewpoint that's just sitting still relative to the distant stars is a perfect inertial frame. You can kind of think of it as the universe's ultimate baseline for watching motion. And this, right here, this is the real revolution. Before them, people might have just said a rock falls because its nature is to be on the ground. That's just what it does. But Galileo and Newton completely changed the game. They started thinking about cause and effect. They didn't just accept that things stop, they demanded to know why they stop. They hunted for the cause. So what's the big takeaway here? It's that things in the universe don't just naturally run down and stop. They persist. They keep going unless something gets in their way. And that kind of leaves us with one final thought to chew on. If the natural tendency of everything is to just continue on its path, what are the invisible forces, the frictions and the pushes that are shaping yours?